Welcome to our Lesson 7 lecture. Lesson 7 is about flow measurements by integrals. All right, so we learned a lot of different integrals this year, and in this chapter we kind of learned about what they mean with flow along and flow across. The first four integrals there, those four integrals all measure the net flow of a vector field along a curve. As long as of course, the parameterization is counterclockwise. Okay. The next three integrals there, they all measure the net flow of a vector field across a curve. Again, making sure that the parameterization is counterclockwise. This is what I just put on there because it's a silly mistake, but it really can change the wording of a sentence. All right, so here's what a student found. And then he wrote, the flow of the field across the curve is from inside to outside. What's wrong with this statement? You might look at that initially and say, oh, there's nothing wrong with that statement, but there is a very key word missing right here. Okay, we have to say the net flow. Okay, flow you can just say is at like a point, but the net flow is all the points combined. So when you're talking about an integral here, you have to make sure you're talking about a net flow across or net flow along. Okay. So here we have another integral equaling 6.25. Interpret this as a net flow along and a net flow across for two different fields here. So this 6.25 being positive tells us that the net flow of this field, positive 3x, positive 7y, along the curve is counterclockwise. However, it also tells us that the net flow of this field, 7y negative 3x, across the curve is inside to outside. Okay, so it really we're talking about looking at two different fields here with one path integral. Sorry, one integral. I know this chapter talks a lot about path integrals. It's in my mind, but this is not a path integral. It's just an integral. All right, so next is the gradient test. Really important here. We know that a path integral for a field, which is a gradient field, is called, what we learned this chapter is path independent. Basically, it means it doesn't matter what path you take from point A to point B. What does that mean? That means if our curve that's given to us is really crazy, we don't need to use it. We can use what's called a substitute curve instead. All right, a field Mn is a gradient field provided that it has no singularities. And the derivative of n with respect to y minus the derivative of n with respect to x equals 0. All right, if a path integral is path independent for a closed curve with no loops, the net flow of the gradient field along that curve is always going to be 0 because it is equivalent to the function value at the start point minus the function at the function value at the end point, but those are the same. Okay, but it is important there to know that the net flow of the gradient field across the curve is not guaranteed to be 0. Could be. Now we're going to look at a couple examples of determining whether fields are gradient fields or not. So the first one here, looking at that, you can pretty easily tell there's no singularities in this. That's the key. That's the first part of this. You have to make sure there's no singularities in this field. Okay, then the second part of this is you're going to take the derivative of m with respect to y and the derivative of m with respect to x and subtract them and see what we get. So the derivative of m with respect to y, that means the whole first part there is just a constant, and you're taking derivative of sine minus, and then derivative of n with respect to x. So you're going to basically take the derivative of the e to the x squared using the chain rule and not taking the derivative of cosine because that's just a constant. And a little finagling there, tells you those two are the same. So if you subtract them, you get 0. So this would be a gradient field. All right, second one, same thing. Again, there's no singularities. And taking the derivative of m with respect to y. This is a little bit more complicated one. You have to use the product rule first. So there's the derivative of m with respect to y. And taking the derivative of m with respect to x. Again, you use product rule in the first part. And a little subtraction, again, that would give you 0. So it passes both parts, and again, this would be a gradient field. Number 3, same thing, no singularities here. Taking our derivative, again, we got to use a little product rule. Actually, no, not product rule, sorry, chain rule for that part, then product rule. And same thing in the second part here. And once again, subtracting will get you 0 for that. So yes, this one also is a gradient field. Save the easiest one for last. Obviously no singularities here. And the derivative of the first one with respect to y minus the second part with respect to x. Obviously 0, so this one is also a gradient field. So 4 examples of gradient fields here. Just so you know, obviously the answer is not always yes. Just wrote down a couple here that were gradient fields so you can see what that would look like. So number 5, we're given a closed curve represented by that ellipse and a field y negative x. Calculate the net flow of the vector field along that curve. All right, so we'll get to that part when we get to that part. First, let's parameterize our ellipse. So x of t is going to be 2 cosine t. Y of t is going to be 4 sine t. Obviously that means t is going to go from 0 to 2 pi. And just because I know we're going to need these later, I'm going to go ahead and take the derivative of both of those as well. That's going to give me negative 2 sine t and positive 4 cosine t. All right, so it's net flow along the curve. So we set up our integral here. We're doing m times x prime plus n times y prime. So that's going to be the integral from 0 to 2 pi. M times x prime n times y prime. Some simplifying of that gives us negative 8 sine squared of t minus 8 cosine squared of t. If you factor out a negative 8 from that, remember that sine squared plus cosine squared equals 1. So we ended up with the integral of negative 8, which is negative 8t. Plugging in 2 pi and 0 gives us negative 16 pi. So to answer our question finally, the net flow along, so I'm going to write that down here. Net flow along, actually let's be more specific. Net flow of this field along the curve, since it's negative, is against the vectors, so clockwise. All right, number 6. Again, a closed curve represented by that ellipse and a field xy. Calculate the net flow of the vector field across that curve. So once again, I'm going to go ahead and first I'm going to rewrite this. As root 3x quantity squared plus y squared equals 1. Give me a little bit more of a feeling about what this is. So when I do my x of t here, it's going to be 1 over root 3 cosine t. And y of t is just going to be sine of t. Okay, and then again, taking my derivatives, x prime and y prime. So the key here is that we're trying to find the net flow across this curve. So when we do our integral, we're going to do negative n times x prime, and then we're going to add m times y prime dt. Okay, and then we're going to do our integral from 0 to 2 pi. Okay, and then we're just going to fill in those blanks. So negative n of x of t, y of t. Remember, n is just y up there. So that's just negative sine of t. Oops. Times x prime. We already got x prime is negative 1 over root 3 sine of t. Plus m. M is just x. So that would be 1 over root 3 cosine of t times y prime, which we got is cosine of t. All right, this is going to simplify very similar to the last one here. So we're left with 1 over root 3 sine squared plus 1 over root 3 cosine squared. And if you factor out the 1 over root 3, we're left with sine squared plus cosine squared, which is of course just 1. So we can get down to this. And then we take our antiderivative, we get t over root 3 from 0 to 2 pi. So our final answer here would be 2 pi over root 3, which is positive. Really, that's all that matters here, is that it's positive. We don't actually need to know what the number is, as long as we know that it's positive. So what does that tell me? It tells me the net flow of the field xy across the curve or across the ellipse, since it's positive, is with the vectors, so inside outside. Brings us to our last page. Just a couple examples here. Find a function whose gradient is that. So there's a couple ways to do this. What I like to do is I like to integrate the first part with respect to x and integrate the second part with respect to y let's see what that gives us. The first part with respect to x gives me x squared y minus 3x plus c. The second part with respect to y gives me x squared y plus 4y plus c. And then after you do that, any term that's a duplicate, you don't have to write twice, just write it once. Any term that's not a duplicate needs to be in there as well. So f of xy could be x squared y plus 4y minus 3x plus any number you want to write. Plus 7, plus 0, minus 100, whatever, doesn't matter. All right, so any constant there at the end would be fine. Okay, that's for 2 dimensions. To do it in 3 dimensions, it's the same thing. Okay, integrate the first part with respect to x, and that would just give me 2x squared over 2, which is x squared. Integrate the second part with respect to y. Same thing, that's just going to give me y squared. And integrate the third part with respect to z, and that's just going to give me negative 4z. So one example for what this function f of x, y, z could be would be x squared plus y squared minus 4z plus any constant minus any constant that you want over there. So you can write plus 4, you can write minus 6, you can leave it blank, it doesn't matter, as you remember probably from BC. All right, the last question here, I just want a couple fill in the blanks just to kind of remind you what some things you hopefully learned in this chapter here. If field Mn is a gradient field, the most important field of all, and C is a simple closed curve, the integral across along C of M plus N will always be 0. And if field equals Mn is a gradient field and C1 and C2 are different curves that start and end at the same point, then those two integrals must be equal. Okay, and that's what we learned earlier. It's called path independence. And why is that important? It's important when you have a really difficult path to parameterize, and you know that it has path independence, you can use a much more simple path of whatever you like. And that ends Chapter 7's lecture. As always, let me know if you have questions on anything moving forward.